Good morning. Good morning. Thank you for
Good
your.
morning.
Oh, good morning. Good morning. Excellent.
Morning.
Great. Good morning. Great to see you
Morning.
all. Great to see you all. Thank you for your indulgence. Give me a second. The board is not here yet. Hold on. I love the. This is great. Uh, okay, this is great. Oh, wait, what happened? Okay, hold on one second. I appreciate the. I know it's. All right, just give me one second. I know the plagues have come early this year, so to speak. All right, you all are to be congratulated and thanked. Um, I will actually try to be efficient today. Just hold on. I know things are happening at once. Okay. Um, the board is.
You like my new look?
I actually thank you for asking. I very much do, as a matter of fact. Yes. I
Thank you, thank you.
It helps a lot. And I see, and there's, okay. And I would put more people in I don't know, this only fits 4 people. Otherwise, Angel and Camilla would be down there too. But no, I very much like the look. Hold on. And
It's okay. How do you jump down there when there's a seat open?
the- how do you, I just literally move you down, but here, in fact, okay, wait, this is so silly. I know, but hold on a second. Hold on. This is so, but it's so much fun. Hold on. I think, no, wait. Here, let's do this. Yeah, so there we go. Okay. But I'm putting up the stall is that my board did not go up the way it should. Hold on, it will. And then that'll kick people out accidentally. And we will get rolling. I have things just, well, of course I have things just. Okay, are we there? Are we there? Are we there? It's Judith. Good morning. Good morning. I haven't even said good morning officially yet, have I? All right. So yeah, okay. Um, oh, there's G. Okay. So let me do this. Oh, there's Angelina. Okay, people still coming in. Um, so yes, so good morning, Jocelyn. Good morning, Angel. Good morning, Gabriella. Good morning, Justin and the new look. Good morning, Camilla. Good morning, Judith. Good morning. Did I say Chanel? Good Veronica. Good morning, Jacqueline. Good morning, Teresa. Good morning, Brianna. Good morning, Gabby. M. Good morning, Lillian. Good morning, Jibo. Good morning, Genesis. Good morning, George. Good morning, Jadine. Oh, we have a full house. Good for you guys. I'm very impressed. Seriously, on quick chat and quick board. Oh. Okay, I see the direct chat about the Wi-Fi. Got you. Thank you. Appreciated. Good morning, Zebo for the double. Good morning, Jocelyn for the double. Jacqueline for the double. Camilla. Good morning, Veronica. Good morning, direct chat person about the late. Obviously, no, you're fine. Gabby M, good morning for the double. Teresa S, good morning for the double. Brianna, good morning. Jadine, George, good morning. Liliana, sorry, Lillian, good morning. Genesis, good morning. Okay, who else am I? Okay, and now the board, and we will get. Where's the board? Where's the board? It should be. And the board is going to knock out people. That's the only unfortunate, I think, or maybe not. Okay, that's fine. Okay. So we're gonna like start learning in a second. That'd be nice. But let me say a couple of quick things. Like, so when I say the plagues come early, you've all been working very hard over the weekend. I know. I mean, it's probably not your favorite weekend of it. I'm very proud of you all. I'm not saying this based on outcomes or results or anything like that. I'm proud and happy for you that for the most part, you're on the other side of something that I think was sort of large for some of you. I mean, I was getting some kind of communications from certain people during the weekend in other sections, but also specifically yours. Um, so it couldn't have been fun or easy. It sounds like people worked very hard. Uh, so I appreciate that. Um, glad you're on the other side. It's also very impressive that you are here after something that exhausting. It's doubly impressive that you would put up with another electronic class. I'm not pleased about it either. I'm going to try. I have a goal for today, which will hopefully not be stressful. I know we're probably running on like low fuel. Again, it's noteworthy and impressive that you're even here, especially for an electronic class. Obviously, I'm in a sick household right now and juggling some things as well. So I feel your pain. I mean, it's different pain. I'd still rather be me than you, probably. But I want to also note quickly. I want to note quickly. So there's nothing. We're not going to talk about the exam today. There's nothing to talk about, right? Yet. But I do know. Wait, you are this class. I do know. I'm looking right now. I'm like looking. Yes, I do know that for the overwhelming most part, I have an exam from each one of you, and or I have a personal arrangement that was made in a couple of cases and it was communicated, which I appreciate the communication. And if it wasn't you that had an exceptional circumstance this time, it might be you that has an exceptional circumstance during the final, or gets an exceptional letter of recommendation from me down the line. Like everybody has an individual life. But what I'm trying to say is I'm looking right now and I see that they are in, for the most part, uh, and certainly at a large glance, look thorough and neat and clean and careful. Thank you. And you're here. So that's great, really. Wait, and someone just entered also, I think. Yes. Okay. Oh, wait. Uh, wait. Oh, uh, hold on. Something in the chat. Um, oh, okay. Interesting. Wait. Oh, okay. Happy birthday in advance. All right. So there's things in the chat. Some are public, some are not. As far as the public, Angel, well, happy birthday in advance. As a matter of fact, it happens to be my wife's birthday today too, which is complicated because she's caught in an airport while her sick child is caught with me. So happy birthday. So yeah, but as far as your birthday, Angel, honestly, the good news is I could see why you would ask that after last semester. But given the new system, for good or for bad, yes, you guys, I mean, I'm not going to say tomorrow, but you should be getting your exams back fairly reasonably, a lot more reasonably quickly. Like, they shouldn't take me much longer than the homeworks have been taking me. I dangerous to say. But yes, if Angel is asking, are you going to get the exams back before the beginning of April? Yes. It's always dangerous to say anything like that, but that's the idea. Things have been going faster for this semester, and that right. So yes. But then, oh, thank you. I appreciate it. Thank you. But now also there's a direct chat thing about. Okay, I see the direct chat about. Well, I'm just going to respond directly. Uh, hold on, and then we will get rolling. But there are some concerns in the direct chat, and they are direct. Hold on. Okay. And someone's here. Okay. All right. So what I'm going to tell you is, so obviously I'll have. Okay, got you. Direct chat. So things are happening. Got you. Direct chat person at the camera. Got it. Thank you. Appreciate it. So okay. So I know it's like intense times. And yes, the main goal here is for me to get the exams back to you a lot, like not in a day, but in a lot quicker than last before. And then we'll talk about them substantively and all of that. But right now, I want us to all breathe out and breathe in a different direction. Of course, look, believe me, as a father or as a human, what I'd love to do is just give you class off today. But I can't do that. I can't afford, especially when I found we can't. We're doing too well in the curriculum, and you guys meet too infrequently for me to just give you the class off. But believe me, I was tempted. So, but what we're going to do instead, we're going to move on with the material as promised. We're going to start a new topic today as promised. However, let me be clear, please. And you all, frankly, as usual, you guys seem actually kind of more awake and alert and human than I would expect under the circumstances. It's noted and appreciated. What we're going to do is start the new topic, but I'm specifically doing it in a way that my goal is actually just to give you everything you need to have on your paper, in your documents, and at the sort of front of your mind before you enter the lab this Wednesday. My main focus today will just be to like equip you for the lab this Wednesday. The lab this Wednesday will be a board meeting, for good or for bad, to introduce the new topic. And I'm telling you right now, I want to say this clearly. Like, people have mixed feelings about board meetings, and sometimes they go better than others, and yada, 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 all that. And sometimes all that. And sometimes physics can be stressful, all that. I'm telling you right now that the purpose of the board meeting Wednesday is to get practice and familiarity and like upfront exposure to like the new big equation that starts the new topic. And I'm telling you right now that for the most part, the thing that you're going to do in the board meeting and the thing I'm going to prep you for today is actually a plug and chug. Yes, you'll have to draw diagrams and stuff, but it is not a trick. It is not a trick. It is more of a plug and chug than usual. We're bearing in mind that you're exhausted. So I don't want to, fool you or anything, but you don't look for tricks or weird subtleties or anything like that. The idea is for me to present this new equation today in a moment and have you, and some of you have seen it before in chemistry anyway, by the way. So you're going to have it in front of you, have the concept, and then you're going to practice that equation in the board meeting on Wednesday. So it, that's so hopefully you could sort of relax with this material once I get going in a second. You if you just stay with me and like operate at like 65% of general mental capacity and think of your goal as getting everything down or getting pieces together so that by the time you're awake on Wednesday you can do it. That's the idea. Okay, and if I get through all of this today somewhat efficiently, maybe we even okay. Well, it's not ideal gas law, but it's close. It's not ideal gas law. You'll see. Well, so the goal is electricity. Okay, what we're trying to move now to is electricity. You might think you never learned about that in chemistry, but you learned about electrons and protons in chemistry. You'll see what I mean. Oh, Gauss's law. Well, that's very good. Wait. Okay. So you'll see Gauss's law. It's funny that Justin, I'm seeing Angel and Justin and so forth. Gauss's law is actually the ultimate real point here. And Gauss's law is deep and heavy and is central to the course, yes, but that's not what's happening this week. This week, we're getting at something called Coulomb's law, okay, which again, I think and maybe you've seen it in high school, many of you. Um, Coulomb's law is the building block to Gauss's law. And for in terms of this week and everything, it's not crazy calculus or anything like that. I mean, there's some so none of this is to minimize it, but just to say, I'm bearing in mind, like I know, or I'm guessing where you are mentally right now. So that is built into what I'm going to try to accomplish today and Wednesday. So, okay. Um, so that said, okay, here comes the board, right? Okay, and I'm going to switch the view in a second. Oh, just check. Okay, hold on. And there's things in the chat. Okay. Okay. quick last thing for context. So, once you, so I'm good. This is like where we're going, what's on the board here, where we're going, not where we've been. Long also summary of everything I just said too. What I'm also trying to say is that whatever is left in your soul or your brain or your stomach from all the exam material, like you can set that aside now, whether you feel proud of it and comfortable with it or shaky with it. You don't directly really need any of that for what we're about to do now. It's a gear shift, and that might be good news for some of you, maybe. What's the connection though? Why are we what does this new topic have anything to do with Physics 204? One quick thing I want to say is this is our next big unthingy exploration. This is the next version of an unthingy kind of phenomenon. We're going to be looking again at, or a different example of how information actually occupies space and time rather than how matter occupies space and time. Like that's the tie-in. That's why this is like all relevant to the course. But so electricity, which is where we're going to head to with this, is another example of immaterial occupation and motion through space and time. Okay, that said, what I first need to do, so here we go. So the new unthingy topic is action at a distance. We're going to try to, by the end of today, we are going to nail down the universal electrostatic force. But in order to do it, I'm going to either tell you or remind you of some background about the universal gravitational force. So bear with me. I'm going to back up first and explain to you how gravity works. Now, to some of you, I did this at the end of last semester. To some of you, we didn't. But I'm going to act so it may be this again. This might be sort of review. Hopefully, it won't be that stressful. But I'm going to act as though it's the first time you've seen it. In relation, I'm looking at the chat. Yeah, right. Good. Huh. Right. Yes, to the chat. Okay. So here we go. Newton's first, first, Newton's law of universal gravitation. Here's the setup. And and there's Justin for real. Okay, that's awesome. That probably happened. Yeah, awesome. Okay. Okay. So the idea behind Newton's universal gravitation is if you have any bit of point mass, call it M1 over here, somewhere in space, somewhere in the universe, and you have another little bit, another point mass, call it M2 over here, somewhere else in space, and they're separated by a displacement vector called r, right? That's the given here. You have a bit of mass over there, you have a different bit of mass over there, and they're separated by a displacement r. The claim of Newton, the belief that we have, known as gravity, is that automatically M1 will exert a force onto M2. And in fact, by virtue of Newton's third law and everything else we already know about physics, M2 will also exert a force on M1 automatically, as long as M1 and M2 exist. So what I want to give you now is the mathematics to tell you the magnitude and the direction of the force vector that is exerted by M1 onto M2, as long as M1 and M2 exist, and as long as they're separated by some displacement called R. One quick thing before I turn the page and change the view. When I say M1 and M2 are point masses, that means they are, each of them is a certain number of kilograms, but like shrunk or packed into an extremely small volume. That's when I say a point mass, I mean a certain amount of mass, but taking up very, very little volume, like a Euclidean dot. Okay. But we write M1 and M2 sort of differently to emphasize these are two arbitrary points of mass. So even though they're both the same size in terms of volume, they are likely to be different numbers of kilograms. Whichever one happens to be a bigger amount of kilograms, we tend to designate capital M1, and the smaller one we tend to designate lowercase m2. Okay, and then they're separated by a displacement vector. Yeah. And good point about, yeah. So our vector is the displacement from, as Justin is saying, from like the center of one mass to the center of the other. Although really, to be really technical, I don't even really have to say center at this point because we're just talking about two dots. They don't even really have centers. They just are centers, if that makes sense. But yes, R is the displacement vector that specifically points from whatever we're calling M1 to what we call M2. That's the given of the situation. That would be step one DFP, so to speak. And sorry, and reminder now, a little bit of reminder from some of the math we were doing, a few weeks ago. R is a vector. It has an arrow written over it. So a vector at this point in our life, we don't just we view in English as a magnitude and a direction, but mathematically we view that magnitude and direction as expressible as a monomial, together expressible as a product of two separate terms. One term is just r that doesn't have any symbol over it at all and refers to the raw magnitude of the r vector, right? In other words, the distance in this case, and it's multiplied by r hat, where r hat, remember from a couple of weeks ago, r hat is a unit vector. So it specifically has length 1 by definition, but it has a direction. What's the direction in this formulation, in this context? It's the direction that points from whatever we're calling M1 to whatever we're calling M2. So r hat is the direction of the line connecting M1 to M2, and r is the length of that line, the distance of this whole spatial separation. Okay, that's the given. I'm being a little overly technical about the vector aspect, but that's the given. According to Newton, M1 will exert a force onto M2 whose magnitude, so a force is a vector, right? A force is a vector. It has magnitude and direction. The magnitude will be given by the computation of all of these letters inside the parentheses, and the direction will be given by that unit vector r hat. Okay, so I'm gonna first say it in that direction. I'm gonna say so m here. I'm gonna put a little. Sorry, did someone just? Okay, I'm going to put a little g here to make it really clear that we're talking about the force of gravity exerted by mass 1 onto mass 2. The force. Wait, sorry. There's something in the. The force of gravity is a vector. It has magnitude. Oh, that's a really good question. Okay, Angel's question. Yeah. Okay, and I could get into more detail of this in a few minutes, but okay, really good question. So Angel is asking, like, wait, hold on, how does this relate to like the lowercase g, the free fall thing that we've been talking about for a semester and a half? Really good point. Okay, two, two, uh, uh, two things. One, what we've been talking about for 2 semesters is the effect of specifically Earth's gravity onto any object that's near the surface of the Earth. What we've been saying is that the center of the Earth pulls on any and every object that's anywhere near the Earth, and pulls all objects with a force that seems to be dependent on how massive they are, and ends up causing all objects to accelerate down at the same rate of approximately 9.81 meters per second squared. So 2 things. One, this is a very important question, very good question. One, anything about we've been saying about gravity up until now has been Earth surface gravity. the gravity that specifically Earth seems to exert on objects near it, for whatever reason. We just notice that it does that. We haven't made any pretense of a reason or anything like that. And number two, every time we've written lowercase g, what we've been referring to is the resulting acceleration under free fall due to that gravity. Now, I am backing up, and I'm saying this to everybody. Again, like, this is a good question. I could have perhaps decided to just answer this question like at the beginning when I was speaking, like before any particular student. So this is for everybody. You might even want to write it down. I'm saying up until now, lowercase g that we've been using has been referring to the phenomenon of Earth gravity. And the lowercase g specifically has been referring to an acceleration, a constant acceleration, constant anywhere near the surface of the Earth, measured in meters per second squared. Now, I am backing up and saying, or Newton is backing up and saying, you know what? Another extension of Galileo's principle, it turns out it seemed like the Earth was doing something special to all objects near the Earth. We didn't know why. We weren't pretending to claim we knew why. We were just noticing that Earth always seemed to pull everything toward it. Then Newton backs up and backs us all up and says, you know what? It's actually, if you really take Galileo seriously and you take this whole idea that Earth isn't some special thing at the center of the universe, like sitting still and pulling everything toward it, if you actually take seriously the idea that Earth is just another rock hurtling through space, past the sun, past other objects like anything else, right? Which is really the big lesson of Physics 203, that Earth is not special. If you really take that seriously, it turns out it's so not special that it does not create its own special force that pulls everything toward it. There's a force permeating the whole universe that pulls everything towards everything. Every little bit of Earth is pulling on every little bit that's near the Earth, every little bit of the moon, every little bit of the sun, and similarly, every bit of the sun is pulling on every bit of Jupiter, et cetera, et cetera, et cetera, so that apparently everything in the universe is pulling on everything else in the universe through a phenomenon called gravity. And the calculation of that force of universal gravity, the calculation of that force involves a number I'm about to say more about, a number that is designated with a capital G. And that constant, capital G, well, yes, as it's written on the board here, that constant is a universal constant. You don't have to memorize it. You will automatically, accidentally, if you do enough physics, but you don't have to memorize it. But you have to be aware that this capital G that I'm now giving you is, to be very explicit to Angel's very good question, this capital G is not the same meaning or amount as the lowercase g. This capital G is getting at the idea of gravity in general through the whole universe, and is a constant number that allows you to calculate the force between any two objects in the universe. It's not an acceleration. It's a constant of force proportionality, and it's not specific to Earth. It's for the whole universe. Bottom line summary. I know that was long, but that, again, the summary is everything we've been saying about gravity up until now, the lowercase g has referred to Earth and has referred to an acceleration that is constant on Earth. We are now expanding our understanding to the whole universe and to the force in general, not just the acceleration. Hopefully that, could anybody, well, including Angel, but could anybody, because I really want to emphasize that was like a good, like that was not just for, so can anybody raise their hand if that made sense what I just said? Like we're transit, okay, thank you, Jocelyn, awesome. All right, awesome. And other people I see, but it got, Justin, great. Camilla, Judith, great. There's other people, Chris, great. Teresa, great. Thank you, Genesis. I hope you're all giving yourself points for that. Awesome. Veronica, thank you. Okay. Chanel, thank you. Excuse me. Okay. Oh, wait. So, okay. And I am going to move on to say, wait, it's like about T times. Yeah, I'm not. I think I want to say yes. I'm about to get to that. I think I'm not sure I totally understand that follow-up question, but yeah, I think the answer is yes, and I think that's what I'm about to say. I think you'll see. So what I'm going to say is this: you have any two bits of mass at all anywhere in the universe, okay, and they're separated by displacement r. Well, to cut to the chase, yeah, okay. And I'm going to get back. Believe me, I'm going to do the math in a second. But what we believe conceptually is that M1, will automatically make a force vector, will place a force onto M2. And because force is always a vector, it will have magnitude and direction given by this equation that I'm trying to teach you right now and that we're going to build electricity from. Okay. This equation tells you how to compute the force vector of gravity given two masses separated by a certain displacement. And again, remember, notice in this equation, there's two r's in there. It's a little confusing at first. One of the r in the denominator doesn't have any arrows or anything over it. That is literally the distance r. That's the magnitude of the force vector r. But the other r, the r hat, is the direction of the force of the displacement vector r, right? So r with no symbol above it has magnitude but no direction. R with a hat over it has direction but has magnitude 1, right? Like, remember, again, the whole assumption of this, in other words, the two r's that you see in the equation are two different pieces of information, of the one big r vector. So how does this work? That equation is telling you what the force vector will be exerted by M1 onto M2. How do you think of it? This is how you think of it. Say you've got M1 over here that's 25 kilograms, and you've got M2 over here that's 2 kilograms, and say the distance between them is 5 meters, let's say, okay? Then the idea is you've got this displacement vector R that points from M1 to M2. So again, it has direction and magnitude. The first thing you think of is you imagine in your mind a little unit vector called r hat. It's a little confusing that hold on, let me make it a little bit. Yeah. Hold. Yeah. I'm trying to say. Right. Okay. Like, you imagine a little arrow of length 1 that points from M1 to M2. That's the r hat unit vector. It's a unit vector. It just has length 1, so it doesn't tell you anything about sizes or anything like that, but it's deliberately designed to say, oh, the direction that you'd have to walk to get from M1 to M2 is that away. So it's a pointer for specifically direction. So you consider that unit vector, right? It has length 1, it points from M1 to M2. Then what you do is you scale that vector. Now you want to give it size. You're going to stretch it or you're going to shrink it by a certain amount. And once you stretch it or shrink it, you're going to and multiply by certain units, you're going to turn it into a force vector, the gravitational force vector. What amount do you stretch it or shrink it by? You stretch it or shrink it by everything that's in the parentheses. So what I'm trying to remind you is that we're thinking now of vectors, we're thinking of vectors as unit vectors that we build, and then we stretch or shrink by certain amounts. That's why we call those amounts scalars, because we have unit vectors and then we scale them by a certain amount. What's the amount? The amount is gmm over r squared. What does that mean? It means that we're going to plug in all those numbers. And literally, it is just a plug-in. I'm sort of over talking it as usual, but it is just a plug-in. So we're going to plug in the mass of M1. We're going to, in kilograms, we're going to multiply by the mass of M2 in kilograms. We're going to divide by the square of the raw distance between M1 and M2. So in this case, that's 5 meters squared, right? We're going to multiply all that together. And then we're going to take that whole package and multiply it, as you see in the white is what I'm talking about here. We're going to multiply the 25 by the 2, divide by the 5 squared, and multiply the whole thing by this 6.67 times 10 to the negative 11th universal constant. Now that's a crazy number, but it is a real number. It's not arbitrary. It's not an arbitrary example. It would always be that specific number, 6.67 times 10 to the negative 11th. And notice, so in other words, I'm talking about, so you multiply m1 times m2, divide by r squared, and then you always then multiply by this number in red, the 6.67 times 10 to the negative 11th. And notice it has units. At first, it might look like the units are crazy or like unnecessarily complicated, but they're not. They're exactly as simple as they should be in order to achieve the desired result. That is, if you look at that number that I'm talking about, if you look at this, the G, the capital G number, you notice that okay, one second. It has in the numerator meters squared. So it cancels out the meters squared that are in the denominator that you get when you multiply R by itself. And then it has in the denominator kilograms squared. So they cancel out the kilogram squared that you get in the numerator multiplying, M1 by M2. And then it has newtons. So the point of the universal constant is it's a constant of proportionality. It scales everything and gives the correct size for MKS or SI units. That when once you multiply by G, that cancels out all the units other than newtons and ends up, and I see there's something in the chat, I'll get it in a second. What I'm saying is to think of where the gravitational force vector, how it gets constructed or thought about is you have a mass 1 over here, mass 2 over here, mass 1 creates a little unit vector that points to M2 and has a size of 1. Then that unit vector gets scaled by all of these numbers. Oh, okay. Thank you. All right. Fair enough. Thank you. That unit vector gets scaled by all these numbers. G, M1, M2 divided by R, raw R squared. So now you have what turns out actually to be a really, really tiny arrow, because 10 times negative 11 is a very tiny number. So now so when we scale this arrow, we actually tend to scale it down, not up, if that makes sense. But anyway, so now we have an arrow that points from M1 to M2, and it now has units of newtons. So now it's a force vector. We've built a force vector from a displacement vector, right? And then the final step, just in terms of considering all this, and you look at the calculation, right? I mean, all I'm doing is plugging them. I'm trying to explain what the plugin is like doing. So I plugged in all those numbers to figure out how to scale the unit vector. I got like 1.33 times 10 to the negative 10th newtons times r hat. What is r hat? It's a vector that points from M1 to M2. But then there's a negative sign before the whole thing. Like there's always a negative sign in the equation, in the law. There's always a negative sign. Why? Because now that negative sign says, okay, you've got this vector, right? You've got this force vector now that you built from a displacement vector. You've got this force vector that's pointing from M1 to M2. The negative sign says, okay, flip it. There's a negative sign. It says, rotate that arrow by 180 degrees. So the arrow was, by convention, by originally was pointing from M1 to M2, but now the negative sign says flip that arrow, so it's pointing from M2 to M1. And I will get the chat in a second, but the negative sign is now saying, is saying that the force exerted by 1 onto 2 actually points from 2 to 1. Please follow this. The negative sign, like the r hat, meant that the whole thing points from M1 to M2. But then the negative sign flips that and means that the whole force is pointing from 2 to 1. Why? Why am I like getting bogged down in that? What's it? Because that means that the force that M1, that the first mass exerts onto the second mass, the force points back onto the first mass i.e., the force is a pull, not a push. The force brings in the other mass toward whatever's creating the force. It's attraction, not repulsion. I'm saying the gravity law. I'm going to turn the page in a moment, obviously, and I'm going to look at the chat. And I'm being highly technical here in a way. But I'm saying the law of gravity is an equation to create a force vector from a displacement vector. And always the gravity law will always have a negative sign in it, because if you actually understand how these unit vectors are sort of working and stuff, you'll see that the negative sign always means that the force from me to you must be directed toward me. That's what the negative sign multiplied by the unit vector means. So the negative sign is always there and always means is always there in the law of gravity. And that means that the force of gravity is always attractive, is always a pull. Of course, you knew that. But now I'm telling you how we get that across mathematically is with a negative sign in concert with a unit vector. So it says it here. Yeah, we have a my handwriting is, whew. It says we have a force vector that gets flipped by the negative sign so as to point toward M1. Again, I'm going to say one last time, I'm going to breathe. I'm saying the unit vector R hat pointed from M1 to M2. That's what R hat means. The displacement from whatever mass we're talking about to whatever the other mass is. But then the negative sign will flip the direction of that vector so that we always get a pull. Let me just, I'm going to look at the chat. Oh, yeah. Okay. So that's what this says in sum. So at the end of the day, at the end of the day, the force exerted by M1. So the force exerted by M1 onto M2, like we wrote F1, 2, like on purpose. F1, 2, the force exerted by M1 onto M2 points toward M1. It is net in the case of in the case of gravity, which is what I'm right now talking about. The negative sign means sorry. So in the case of gravity, we always have a negative sign, because what negative sign? If you follow this logic, the negative sign always means attraction / pull, as opposed to repulsion / push. Okay, now, let me look at the chat questions. Hold on one second. Oh, already answered. Okay. Is the repulsion equal? Right. So what that does mean, so thank you, Angel. Yes. So my big emphasis for the last 2 minutes has been this negative sign. And yes, indeed, I'm trying to set the stage to say from here on in, if you ever see another equation of this kind of form, which you will, if you see an equation that has action at a distance but has a positive sign in it, by all of this logic, what that must mean is it will be repulsion, push. Yes, from here on in, I am saying, therefore, negative means attraction, positive means repulsion. Exactly, Angel. Yes. One other thing I'm going to say, and then move on, is for good or for bad. This is setting the stage for electricity, which is what you really are going to be concerned about in the class and in the lab Wednesday. But also, just to be honest and clear, this pickiness about direction and the negative sign and the unit vector, that we care about in class, but that is not going to be your main focus in the board meeting on Wednesday. The main focus on Wednesday is magnitudes. So if you're triaging mentally and just like trying to like focus on what you need for Wednesday in terms of the rest of what I'm going to say, what you'll need is how to deal with the magnitudes. You won't need to get bogged down in this direction thing for Wednesday. Okay, wait. So wait, someone's here, and then I'm gonna move on, and then there's someone in the chat. Hold on. Right. It's important because right. Yes, it's important because of relation of the situation. Right. The bottom line is this whole sign thing. This whole plus minus thing. becomes important to distinguish between attraction and repulsion, which, yes, differs from situation to situation once we have electricity, as you may know from chemistry. Like, right, I'm setting the stage with gravity right now. Gravity is always attraction. It always works like this, and therefore always has a negative sign. But now, yeah, I'll move on. Oh, okay, okay. A little bit more on gravity here. Sorry, I'm just okay. So a little bit more on gravity. The resulting force vector is a force. I mean, it's a force. And that means everything that we already know about forces from physics, like from first semester, applies. That means the gravitational force, once you calculate it, is one of any number of forces that gets plugged into the left side of F net equals ma. It contributes, it's one of the many contributions that's made to the acceleration of any given object. In other words, if F1 exerts a pull onto, excuse me, if M1 exerts a pull onto M2, now there's a pull acting on M2. Now there could be other things acting on M2 as well, maybe or maybe not. You add up all of the pulls and pushes acting on M2, and together they will predict the acceleration of M2. So like physics still applies, but now also, I want to say Newton's third law still applies. Yeah, I think I may be about to answer your question. The third law still applies. So everything I just said about what M1 does to M2, well, automatically, necessarily, M2 is going to do right back to M1. Same magnitude, opposite direction. Like, as I say, Newton's third law still applies. And also, multiplication is commutative. So anything I was just saying about M1 times M2 would also apply to M2 times M1. The only difference is that then we would look at it from the point of view of M2. And I think this is going to address what I think is in the chat. So what I'm saying right now is M1 is generally the bigger mass and M2 is generally the smaller, but that's generally, that's like a custom. That doesn't have to be the case. What really is the difference between M1 and M2 is whichever one we're focusing on in that moment in our mind as the one that's creating the force, since each one always would be creating a force onto the other. But remember from first semester, like I push the wall pushes me, or anything. You pull on me, I pull on you, always, necessarily. But those forces don't cancel each other out or make each other irrelevant or anything like that, because whatever I do to you causes your acceleration. Whatever you do to me causes my acceleration. Or really, I should say, whatever you do to me goes into a free body diagram of me that may involve many other forces as well. Whatever I do to you goes into a free body diagram of you, which might involve other forces that have nothing to do with me. And your free body diagram makes your acceleration, and my free body diagram makes my acceleration. So, right, so anytime we're looking at what is M1 doing to M2, we could also just shift our perspective, or we will, and say, but what is M2 doing to M1? So wait, so I'm going to look at the chat in a second. I just want to land this plane. I'm saying therefore, really? I'm saying, yeah. So I'm saying the real, and then I'll look at the chat, but I'm saying the real distinction then, whenever I say M1 versus M2, I mean, in a way, it's an arbitrary distinction, but it's a distinction about what are you focusing on at any given moment. So whichever mass you're focusing on as causing the force, oh, okay, sorry. Whatever mass you're focusing on as causing the force, we tend to call M1. And whatever mass is like receiving the force, we and we call that the source mass. The source of the force, we call the source, if that makes. And then whatever is receiving the force, we call the test. It's like a testing the effect of that force. Again, we could shift our perspective and talk, like the other thing is happening at the same time. But whatever we're talking about as generating the force, we refer to as the source, and generally designated with capital M1. And whatever we're talking about receiving, we don't call it a receiver, we call it a test. for reasons you'll see in the board meeting on Wednesday. Okay, I'm going to pause on that for a second. I'm going to look at the chat. Hold on. There's a lot going on in the chat, I think. Okay, wait. Oh, there's like a lot going on in the chat. Okay, hold on one second. Is there I think I got that. Why have to wait, and we don't want to like too much related to chemistry. I mean, isotopes. I mean, that's cool, the word isotopes, but that's
Can I ask my question?
uh, yeah, I was just trying to go in order. Wait. Oh, okay. I did. Yes, please. Yes. Ask your.
Okay. So if both the masses are the same, right? Would it just be m squared instead of like whatever else we were doing?
Oh, good. Yes. If it turns out that both the masses are the same, sure, you'll just square that number. Absolutely. And a corollary to what you're saying is even if the masses aren't the same, certainly the units are going to be kilograms squared, which will then cancel out with the kilogram squared of the G. But yes, if they have the same mass, it would just be m squared. Absolutely correct. Yes. Good question. Good
Wait,
question.
wouldn't it sorry, wouldn't it be zero if they're related to each other? Both the masses would cancel and M2 would just be zero?
Wait, that I'm slightly confused. But the masses are in the numerator. Hold on, I'm just moving back here. The
Yeah, he asked if they have the same mass, if M squared is just like the answer, but wouldn't if you're relating M1 to M2, wouldn't that itself be zero or just the same mass?
Wait, but you're multiplying them though. Why would it? I'm not quite sure where the zero would come from. I mean,
I
you're
think I
not
can
talking.
answer that.
Okay,
I
It's when
just
you
thought
have
like in
two.
relation.
wait. Okay, wait. Sorry. Wait. Wait. Sorry. Hang on, Justin. Hang on for what? Wait. No, Justin. You say the thing you were going to say, and then we'll make sure this gets resolved before. But yeah,
Okay, so I think it's when you have two different masses, but they have the same like mass, like kilograms. That's when you square. But if they're the same, like in the same location, it's zero.
oh. Is that what you're saying, Angel? Oh, okay. Or is that, does that, now right. I
Yeah,
mean,
it's clarified now. That's why it's squared. I just thought in relation that two masses, since they're the same, would be zero relative to one another.
okay. Right. As long as, right. If they're the same amount, it would not be a zero. But you're right. If they were literally at the same spot, if it was just one, if they were both at the same spot so that they end up being that R equals zero, yeah, then R would be zero. That's right. Um, okay, I think we're good. Yeah, okay, cool. Um, okay. So, but cool. And keep this coming. I mean, look, this is better for everybody that people are participating. Believe me. I mean, and again, there's a specific, if we get through what we need to get through, then we'll whatever. Good. I mean, it's better that people are okay. So. Oh, one thing that I think may have prompted all this, or it had something to do with something that Angel put in the chat. Like, just to be clear, like you see my notation, it's kind of like the notation that you guys were doing in Galileo's principle of relativity and the Doppler effect and all that. Like, if I write F1, 2, I mean what the one is doing to the two. But if I write 2, 1, I mean what the two is doing to the one. And yes, I'm asserting, according to Newton's third law or according to Galileo, whatever, I'm saying they better be the same magnitude, just in opposite direction. Whatever the sun is doing to the earth is the same thing, the same number of newtons pull as what the earth is doing to the sun, but just in the opposite direction. So hence this statement at the bottom. Okay. But so the order of the subscripts is sort of telling you what perspective you're looking at it. Okay, so that's all that. All right, so what are the two takeaways? Like, why am I bothering you with gravity suddenly now? Well, in principle, this is a reminder of some old mechanics thing. There's two takeaways from this law. One is a conceptual takeaway and one is mathematical takeaway. The conceptual takeaway is that this gravitation, this is an example of what we call action at a distance. Very unthingy, kind of idea, action at a distance. Action at a distance means no material contact is needed, nor even relevant to the phenomenon. I mean, to believe in gravity in this way, to believe in universal gravitation, is to believe that as long as a piece of the sun exists, and as long as a piece of the earth exists, no matter how far away they are, no matter what's in between them, no matter what they're doing, including doing nothing, they will automatically be pulling on each other, like literally yanking on each other and causing each other to accelerate or contributing to each other's acceleration. Okay, like there doesn't need, and it's not any special property of the sun nor any special property of the earth. It's any bit of mass of any kind anywhere that pieces of mass automatically pull on any and every other piece of mass through the universe, even if there's nothing between them materially, thinginess, or if there is stuff between them. It doesn't matter. So I see there's stuff in the chat, but I'm going to say this first. And that's very important. And that's a very powerful idea. And one of the reasons I have to keep saying it is I'm going to make it sound like it makes sense because I'm going to say it over and over again. And I'm saying that it's reality. I don't mean in any way to imply that it makes sense. In fact, the more you think about it, the more you might find that it doesn't make sense. But I'm saying that it's apparently true that for the sun to pull on the earth, or for a bit of the sun, like at the center, to pull on a bit of the earth at the center, or for the bit of the earth to pull on a bit of the moon, or for the bit of the earth to pull on a bit of some brick. On the one hand, the bit of the earth does not have to reach out and literally grab the bit of the brick. It doesn't have to move toward it or touch it or make any material contact with it. This gravity will still happen. On the other hand, even if you put stuff in between the bit of the earth and the bit of the brick, still gravity will occur. And to be super explicit, I'm saying there's like a coffee mug on my desk, right? I'm saying the center of the earth is pulling on that coffee mug automatically, even without touching the coffee mug. Now, even though I'm not saying I know why, and I'm not saying, duh, like that should be the way it is. I'm just saying, apparently that is the way it is. And furthermore, I'm saying if you put a desk in between my coffee mug and the earth, let's be super clear about those free body diagrams we drew last semester. You draw an arrow for mg, meaning, gravity down, pulling on the coffee mug. But you also draw an arrow up normal from the desk. The meaning of that is that when you put a desk in between my coffee mug and the earth, you're not blocking gravity. Let's be super explicit. When I put a desk in between earth and the coffee mug, I'm not stopping the phenomenon of gravity. I'm not interfering with it. I'm not slowing it down or speeding it up. I'm not having any impact on it at all. It's just that I'm introducing another force onto the cup. So the cup is pulled down by the center of the earth. And if there was nothing else going on, it would fall to the center of the earth. But now there's also a desk pushing up on the cup. So two things are happening to the cup. It's being pulled down and it's being pushed up. So it sits still. But I'm trying to say, you're not eliminating gravity, you're just counterbalancing gravity. Gravity doesn't care about material contact between objects. That is what makes it what I call unthingy. That's what makes it immaterial. It doesn't seem to require any material contact for it to exist. That is point number one. And I do know there's things in the chat. That's the conceptual aspect of gravity that I want to land with you before I move on to electricity. Point number two is what we call this inverse R squared proportionality, that it acts through an empty distance. Gravity acts through empty space. But how it acts is that you take the amount of empty space, you square it, and you put it in the denominator of a fraction. The bigger the square of the distance between the two objects that are exerting gravity, the bigger the square of the distance between the two objects, the smaller, the weaker the force of gravity between the two of them. Again, am I saying, duh, obviously, of course it would be inverse squared? No, I'm not saying that. I'm not saying it makes sense yet or that it should make sense. I'm just saying it's true that gravity has these two qualities: conceptual action at a distance and mathematical inverse r squared. The bigger the distance squared, the weaker the force. That's what we're saying so far. Now I'm going to look in the chat and then I'm going to move on. Well, right. Okay. So Angel, and there's also things in the private chat I'm looking at, but right. So once there's contact, that means we're talking about other forces like tension or friction or normal force. I'm not saying that they get rid of gravity. Like gravity's always there. I'm saying this is why, by the way, sidebar, I used to get like very freakish about this on homework 1A to many of you. Like Newton's second law is not force equals mass times acceleration. It's sum of all of the forces equals mass times acceleration. I'm saying right now that any object, how it accelerates is the result of all of the forces acting on it. Now, one of many forces that could be acting on any object at any time, or one of many forces that's always acting on objects, is gravity. Gravity is not the only force that acts on objects, and other forces can act on objects, and when they do, they don't get rid of gravity. But gravity is the one that we know right now, that seems to act with no material contact at all. All the other forces, tension. So when you see tension act, or when you see material contact, yes, that's producing other forces like tension or normal or friction or whatever. Again, they don't mean that gravity isn't happening, but they mean something else in addition to gravity must be happening. So that's one thing that Angel has in the chat. Wait. And yes, quick side, it is true. If you believe in all that, I mean, physically, if you believe that like everything is pulling on everything, and if you believe the equation saying the bigger things are, the more they pull, and the closer they are, the more they pull. In fact, wait, I'm going to say this too. This is to everybody again. Like we just did one sort of dumb example right here. It's not dumb, but I mean one plug-in example. Notice the answer we got was a tiny, tiny number, because the amount of mass, the kilograms that I was putting in were reasonably small, like 25 kilograms, 2 kilograms, whatever. And the meters were like regular macroscopic 5 meters. If you just put in sort of regular everyday numbers into a gravity equation, you end up getting an answer that's really, really tiny. Small objects don't exert a lot of gravity on other small objects, even when they're pretty close. When the gravity numbers start becoming sort of relevant and having practical effect is when the masses start getting really, really big, like planets and stars. So universal gravitation starts to become much more sort of relevant, and all other things being, in operational in sort of outer space. Okay, I mean, it's always there, and if it were the only thing there, all of us would be pulling toward all of one another all the time. We'd all be smashed together. But there's other forces in the universe also that are operating that we're about to get to. Gravity is not the only one. And in fact, gravity is really tiny in magnitude, all things considered. It starts becoming relevant. It's always attraction, but that attraction starts to become relevant when the masses start becoming very big. So quick thing on one of Angel's things there is, yes, it's true. Like the Earth is always pulling on the moon, and the moon is always pulling on the Earth. That's always happening. But on the outside of all the Earth is a whole bunch of water, right? The oceans of the Earth is like this huge layer on the outside of the Earth, all of this water. And if you're following this equation, and I will shut up in a second, but these are good. If you're following the logic of this equation, that means that wherever the moon is in relation to the Earth, like the moon is pulling on all of these waters, these oceans on the surface of the Earth. But if like here's the Earth right here and here's the moon over here, so the moon is pulling on these waters that are on the close side of the Earth to the moon, but it's also pulling on the waters on the other side of the Earth, but pulling on them less because they're farther away, right? So the moon will pull more on the waters closer to it and pull weaker on the waters on the other side of the Earth. And so that disproportional, that unbalanced pull that yanks the waters, like it yanks the waters toward the moon in an imbalanced kind of a way. And that makes all the water slosh, in the direction of the moon, like on balance, like relative to the Earth. But then the moon later is in another position. So it does that same thing to a different part of the water. So the overall effect throughout the month is what we know as tides. Like the sloshing back, the rhythm and the pattern of the waters sloshing back and forth relative to the Earth is, yes, ultimately because of this continually repeating harmonic oscillation of net gravitational forces on the surface waters of the Earth, ultimately known as tidal forces. So yeah, that's a good example of how real gravity is, and how real this equation is. Absolutely. Okay, sorry. So that's a good point. That is a good parallel. Yes. Oh, and a good parallel to the brains at birth. Interesting. I'll leave that alone. But yes, interesting point. Inverse means that it can be equated to. Oh, the inverse. Every time I say inverse r squared, when I say inverse r squared, I mean specifically that the r squared is in the denominator of the overall fraction, meaning that the force is inversely proportional to the square of the distance, meaning the bigger the distance squared, the smaller the force, and vice versa. That's what I mean by inverse. That it's not direct proportionality, it's inverse proportionality, meaning that the square of the distance is in the denominator, not the numerator. Space vacuum. Okay. Okay, cool. The space vacuum doesn't detract. Right. Vacuum, the whole point of a vacuum is it doesn't have an effect on this. That's right. Or is minimal effect. That's right. Okay. Yeah, right. It's zero. So yeah. Okay. Cool. Okay. So now I'm looking at the time. Okay, so that's the takeaway of gravity. Okay. Okay, so now we transition. Now that we have that takeaway, again, what's the point of all that? Action at a distance, inverse r squared. Concept, unthingy concept, inverse r squared math. All right, so now, like about a century and a quarter later, there's a French physicist or scientist named Auguste de Coulomb, Coulomb, who says, you know what? This concept and this math that applies to point masses also applies in the same or in a very similar way to point charges. Now, mass is an inherent property of matter, of material thingy things throughout the universe. Like, I don't know why mass exists or why things come in packets of mass, but apparently they do. Similarly, if you break things down to small enough building blocks, they come in packets of this other fundamental characteristic known as charge. I don't know why. Charge is like mass in that it is a inherent property of certain things that exist, specifically protons and electrons. It can be measured in certain units that we're ultimately going to call coulombs. The one big difference between charge and mass, and something that every material thing has mass. Only some material things have charge, evidently, like neutrons have mass but don't have charge. Protons have charge and mass. Electrons have charge and mass. One difference between charge and mass that you know from chemistry is that for whatever reason, the way we think about the world, it seems that charge comes in two varieties. what we call plus and what we call minus. I don't know why. Um, I don't know why it comes in two varieties. I know, and I'm going to show you why it sort of makes sense to call them plus and minus rather than calling them red and green or something. And I'm not joking. Like there is like some sense to calling these two varieties, to using math to refer to these two varieties. I'm going to show you that sense. But why there's two varieties of charge and apparently only one variety of mass, I don't know. And also I say apparently, like maybe like we keep studying and keep studying, and someday we discover some sort of equivalent to the opposite of mass or something. I don't, but at this point, this is the way we look at things. I'm gonna wait, why? Oh, wait. Well, wait. Well, actually, wait a minute. Okay, I'm just looking in the chat. I'm going to go on. I'm going to give you numbers in a second. Wait, but what? Wait. Why are you cooked? I think Justin's trying. But what? No, yeah, actually. Oh, I see why. No. Actually, I think there is. Well, wait. We're all learning. Yes, we're all learning. Safe space, all that. And I'm going to give you numbers in a second. But for perspective, actually, in the in the grand scheme of things, of course, protons, neutrons, and electrons are all very small. They're all like in the atom. They're smaller than atoms and they're smaller than molecules and all that. But actually, comparatively, oh yeah, that's fair. Actually, yeah. Okay, wait. All right, everybody slow down for a second. You know what? I was thinking about that a second ago. We good or bad, we actually are going to take a break in a second. Just hang with me for a second. Wait, everybody slow down for a second. I mean, I'm glad that everybody's like really trying. Clearly you are. We are going to take a break in a second. That doesn't mean that we won't maybe end a little early. Like we might. Okay, but we are going to take a break in a second. Let me just land this minor plane right here. I'm not even going to turn the page, but I'm going to say for perspective, um, protons and neutrons are comparatively big. They are big masses for subatomic particles. And they take up space. Like they have size, like they're in the nucleus, protons and neutrons. They're smaller than like light, but for an atom, protons and neutrons take up space. And as you know, the nucleus is like most of the atom, and they certainly have mass, and there's numbers for these masses. Electrons, I'm going to get to this after a break. Electrons have really tiny mass compared to protons and neutrons. It's still calculable. There's still a number for it. Make no mistake. These are all thingy things. Protons, they're tiny. You can't see them with the human eye, but they are like real and material. But electrons, of the three of them, are the ones that are tiny in mass. Hang on. Electrons are tiny in mass. And in fact, if you want, you have to spend a little bit during the break. Electrons are tiny in mass and essentially take up essentially no space. Like electrons are what we consider point particles. They really are just dots. Like they don't have a radius, so to speak. Protons and neutrons have a radius. Like they're small, but they're there. Electrons are really small. Okay, just now, I'm going to leave. Okay, so hold on. I think this is actually perfect because it's like 12:03. I'm going to say for good or for bad, I think we do need a break. I need a break. We're going to start again at 12:15. That we may or may not go the whole way. I mean, there's certain things I have to get to, but if I get to them all, but I'm going to pause the recording, balance your fluids or whatever, balance your brain. We're going to start again at 12:15, as though it's the next period, all that stuff. Okay. Or just please acknowledge electronic hand that thank you. And thank you for reminding me or being honest, whatever. So just give me electronic. Okay. Thank you, Gabriella and everybody. Okay. So I'm pausing the record and everybody. Awesome. Teresa. Great. Rebecca. Thank you. Awesome. I'm pausing the recording. I'm turning off my video and blah, 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 blah. We'll be back in 10 minutes. Okay. 10 minits. I'm starting the recording again. No, I'm not. And I'm going to go back to the view. So, right. Okay. So now we're going to talk about these 2 points. So we're going to talk about charges as though we have like protons over here and electrons over here. In fact, let me be specific. Yeah, fair enough. Yeah. Thank you. Thank you. Let me be specific and say, so we're now shifting gears and saying, apparently electricity works like gravity. Apparently, there is a universal electrostatic force that automatically exists among protons and electrons and protons and protons and electrons and electrons. And we call this phenomenon electrostatics, as in static electricity, as in socks in the dryer and all that. Why do we call it statics? Because we're trying to emphasize that nothing needs to be in motion. Nothing needs to be happening in order for this phenomenon to kick into effect. We're saying if you have a point charge over here and a point charge over there, then automatically, even if this point charge is static, just sitting around, and that point charge is static, just sitting around, automatically this bunch of charge will exert a force on that bunch of charge over there. Now, where do charges come from? Protons and electrons. When I say point from now on, I do mean the same thing as what I meant when I said point mass. I mean that you're going to have a bunch of charge, a high amount, a high magnitude of charge, but compressed into a small volume over here, and then some other magnitude of charge compressed into a small volume over here. And if that is the case, automatically they will interact with each other in a manner that is very much like gravity, only taking into account the fact that apparently charge can come in these 2 varieties, positive or negative. So we're going to get into that in a second. But and given that the numbers are going to be different, but the concept and the numerical relations will be the same. Let me look at it. Yeah. Is it like the same as? Right. So, yes. Quick answer to the chat is yeah. Well, it's like the same, like similar. Yes. Okay. So here's how it works. Any and every point charge, capital Q1, will exert an electrostatic force onto any and every other point charge, lowercase q2. So now we're using q's, to mean charge instead of m's to mean masses. And the forces will be exerted according to an equation that looks just like if you look at it, looks very much like the gravity equation. It has an r hat at the end indicating direction, and then has a big parentheses with a bunch of numbers in it indicating magnitude. The numbers are that you take the amount of charge of one, multiply it by the amount of charge of the other, divide by the square of the distance between them, and then multiply the whole thing by a constant that acts like the gravitational constant, but is a different number because now it's relevant to electricity, not relevant to gravity. And notice now I'm putting an E subscript on everything to reinforce that now we're talking about a universal force of electrostatics rather than a universal force of gravitation. And you'll notice also that the constant, well, I'll get to this in a moment, but well, here you'll notice I don't have a negative sign on the expression anymore because now it could be attraction or repulsion. It's not, we don't know in advance. So there's no sign built into the law anymore. And the constant now is no longer capital G, it's a capital K. And I have to pause on that for a minute. This is the 3rd K that we will have in this class. That's super annoying. We had the K of Hooke's law, newtons per meter. Then we had a different K, the K of angular wave number. So I used to write that with serifs on it to sort of distinguish. Those were 2 different Ks. That was already annoying. Now we have a 3rd K. That's just the way it is. We have a 3rd K now. However, you're going to find number one, we're in a different context now. So usually the other Ks won't come up in this context. But also, there's going to be two other ways we're going to distinguish these Ks. Generally speaking, I'll put a little lowercase e. Yeah. I know. It's like totally annoying. But I'm saying now this K, which will be known as the universal electrostatic constant, right? Okay. Or the Coulomb constant, we'll put an E after it to show that that's what we mean. But also, you're going to see in a couple of minutes, we also generally, there's a whole other way that we generally write it, you'll see. So, but you right. Okay. So even if you don't like the KE, there's another way we're going to write in a couple of minutes, you'll see. So just bear with me. But the bottom line to notice right now is that the force that governs electrostatic conceptually works like gravity in that it just happens. Things, if the minute protons exist or electrons exist, they automatically do this thing of pulling and pushing through empty space, just like masses automatically pull through empty space. And they do so in this inverse R squared form. Again, I'm going to turn the page, but I'm trying to emphasize now that your board meeting tomorrow, Wednesday, will be about this equation. Okay, it won't be about the other, it'll be about this equation. The sheet you're going to get will remind you of the other equation, but it'll be about this equation. The topic is this equation, but I said the other equation first to get that grounding so that from here on in, anytime anybody's talking about a proton or an electron, they're very, very small. They're very hard to picture. They're kind of abstract, right? They are thingy things, protons and electrons. They are material particles, but they're hard to relate to. So one thing we want to remind you as physicists is whenever you're trying to picture what would happen in an electrostatic situation, it helps to always go back in your mind to thinking about like the sun and the earth or something like that, because electrostatics works conceptually and mathematically the way gravitation works in this inverse R squared action at a distance form. Okay, so that's now. Yes. Okay, that's what it says here. So no, the electrostatic force. It's almost like I know what I'm talking about. It's almost like I planned what I was talking about. The electrostatic force works much like the gravitational force. It's conceptually action at a distance, and it's mathematically inverse R squared. So far, there's apparently two forces we now know in the universe that seem to hold together or hold apart the universe, the gravitation and the electrostatic, and they both have this format. But now there's some details that we have to adjust to shift from considering gravitation to considering electrostatics. The first thing is that constant, the Ke, instead of the capital G, the constant is now a very large number. The gravitational constant was a very small number. I mean, it was like, it took a lot to write it out, but it was in magnitude very small, 6.67 times 10 to the negative 11th newtons meters squared over kilogram squared. That was the gravitation number. The Coulomb number, or the electrostatic number, is approximately 8.99 times 10 to the ninth Newton meters squared over Coulomb squared. Now, first of all, okay, notice. Wait. No, I just mean, hold on. I just mean like a conceptual shift. I'm just saying shift. We're just shifting gears. I don't mean it literally. Sorry. I just like okay. That's good though. You definitely aren't paying attention. So the first thing is, I want to know, whenever I say like G approximately equals 6.67 or KE approximately equals 8, I want to be clear. I don't mean approximate like I'm making it up, or that we would change the number every time, or that it's like a kind of, a guess. It's always the same number every time. It's just approximate in that the digits go on forever without repeat or pattern, like the digits of pi. All natural numbers, all universal constants actually do that, have decimal expansions that go on forever with that. And we could compute those digits with a computer, but they go on forever. So we have to chop them off somewhere. So that's what I mean when we say they're approximate. It's not unknown. It's just we're rounding. That's number one. Number two, and it is very interesting to note that natural numbers always do that. And if you ever want to talk to me about that, like that's very interesting actually. But like pi is not the only number that does that. It's just like the first number you ever, oh yeah, happy Pi Day. Good point. That's not what makes pi special. That's just the first time you've ever heard of that concept is in pi. But anyway, the second thing I want to say is that this number KE is a huge number. It's 8.99 times 10 to the positive ninth. Wait, like the Fibonacci. I mean, Fibonacci is another example of that. Yes, yes. 8.99 times 10 to the positive ninth. So this is so electrostatics, all other things considered, are the electrostatic phenomenon is a far more powerful phenomenon than the gravitational phenomenon. Note that. But then also now the units of K are newtons meters squared over, okay, no longer kilogram squared, but now Coulomb squared. Same logic. The meters squared of R squared in the denominator will get canceled out by this. But what's in the numerator of the Coulomb equation is no longer kilograms times kilograms. We're not talking about masses anymore. We're talking about charges times charges, and charge from here on in. The SI unit or the MKS unit for charge is a Coulomb. So from now on, charge is measured in capital C coulombs, and that's what gets canceled out by this constant in order to leave newtons as a unit of force. Okay, so what is a Coulomb? I mean, Coulomb is a unit of charge, but is it big? Is it small? It's actually a very big unit. Here we go. 1 Coulomb is the SI unit for electrostatic charge. 1 Coulomb is, in fact, a very large amount of charge. Well, I mean, wait, careful. I mean, no, I'm saying the constant is in newtons meters squared over Coulomb squared. So then when you plug this in, we're going to do an example. You're going to do an example in the lab. If you plug this into the equation and then multiply by an amount of coulombs, Q1, and multiply by another coulombs, right. Oh, okay. Okay. So I'll go, all right. So yeah, so the units of this constant make all the units cancel out except newtons. They make it so that at the end of the day, what you're left with is a force measured in newtons, just like gravity makes a gravitational force measured in newtons. Okay. And same idea, by the way, as gravity, that you think of a unit vector pointing from one to the other. Sorry, wait. So you think of a unit vector pointing from one to the other, and then you scale that unit vector by charge times charge divided by meters squared times this number. And this number makes all the units work out so that you scale that unit displacement vector and turn it into a force vector measured in newtons. That's what the constant does. And then to answer the question in the chat, 1 Newton is 1 Newton of force is 1 kilogram of mass times 1 meter per second squared of acceleration. Like literally, 1 Newton is 1 kilogram, because F net equals ma. 1 Newton is 1 kilogram times 1 meter per second squared. So in English, or like in perspective, that's about the amount of force that it would take to hold an apple in your hand, and get it and shove it quickly enough that you get it going from 0 miles an hour to about 2.5 miles an hour. I'm saying that just for perspective. So if you go like that, that's a Newton of force. Okay. Yeah. So 1 Coulomb is the unit for electrostatic charge. It's a very large amount of charge. How large? I'm going to tell you. Remember that what creates charge is protons and electrons. The amount of, and what you may remember from chemistry is, what protons and electrons are different sizes and they like live in different places, but the amount, thankfully, one simplifying aspect of the universe is that the amount of charge in a proton is equal but opposite to the amount of charge in an electron. Hold on one second. Sorry. Sorry. 1 second. I'm getting. One second. Okay. Uh, okay. Okay. Sorry. So the amount of charge of one proton is 1.60 times 10 to the negative 19th coulombs. The charge of one electron is negative 1.60 times 10 to the negative 19th coulombs. To be clear, oh, awesome. So you remember, okay, great. You remembered that. So, and all of these numbers I'm giving you today are for a number of it. One, just so that you're familiar and it makes Wednesday easier for you, but they're all going to be on the sheet that you're given Wednesday. Okay. I'm definitely not saying you have to memorize all this, but it is good to have this perspective to see how this all works. So one thing I want you to see right now is the amount of charge of a proton, if you measure it in these units called coulombs, is a very tiny amount of charge. I mean, the quick reason, we've figured all this out, like the way you live life forwards, but you figure it out backwards, like for real. Like and so it's scientific. People studied all this by looking at charge flowing through wires, as you will start to do next week in the lab. Like you're going to be in the lab having the same experience that the early physicists and chemists and so forth had, which is that it's easier to deal macroscopically with things. So they first discovered huge amounts of charge moving through wires in a phenomenon known as electrical current, which comes from this, but we actually discover first. So honestly, you're going to do this math, this board meeting this week, but then once you start playing in the lab, you're going to go straight into like electrical currents and stuff, just like the early days of physics did, because it's easier. It's more accessible to the human body to look at large macroscopic phenomena. So you'll look at large amounts of charge running through wires. And then, but from that, we sort of backwards engineered or backwards discovered the tiny bits that are making it up, known as electrons. So our scales for talking about all these things kind of went in the order of history rather than perhaps the order of what you might consider logic. What I'm trying to say is that protons are what make up positive charge and electrons are what make up negative charge. The amount of charge in an electron, if you measure it in the SI units, in the units that we now use, again, for historical reasons, the amount of coulombs of charge that's in an electron is this preposterously small amount. Negative 1.60 times 10 to the negative 19 coulombs. What that means, yeah, ACTC. What that means is that if you're given a problem in physics, as you will on Wednesday be given a problem, where they talk about like a coulomb of charge over here, or 5 coulombs of charge over there, or 50 coulombs of charge over there, those are numbers that are nice and easy to work with, but they are in fact enormous numbers. If you think about it, one proton is like 1.60 times 10 to the negative 19th coulombs. Therefore, wait, yes, you are. Yes, yeah, totally you are. Next week. Yes, good question. So therefore, flip that logic on its head. If I say here is a 1 Coulomb point charge, what I mean is you have approximately 16 quintillion protons jammed together in a tiny, tiny, in less than a cubic millimeter or cubic angstrom of space. That's a lot of protons in a tiny space. Is that an impossible, imaginary number? No, it's totally possible, but it's large. Generally speaking, realistically, in the lab, what you play with, really realistically, in a lab or in currents and stuff, are like millicoulombs or milliamperes of current. Like you'll generally really play with things like 1,000th of a coulomb of charge rushing past you every second or something like that. I'm just trying to be realistic so you understand what's going on, right? Which would mean not 16 quintillion, but like 16 quadrillion protons jammed together. Now that is realistic. Like protons are very small, or more particular, electrons are very small. To have a quadrillion of them jammed into a tiny, tiny space, not totally possible, totally realistic. But that's what you want to picture from now on. I'm going to move on in a second, or look in the chat, just so you understand what I'm talking about. When we say a positive 1 coulomb of point charge is over here, what we're asking you to picture is like like 16 quintillion protons jammed together and sitting there. Or your 16 quintillion electrons, which is a little bit easier to picture because you can dislodge them from atoms and you don't have to like do nuclear physics to get electrons. When we say a coulomb of negative charge, we're asking you to picture like 16 quintillion electrons put together in like a pin of in the head of a pin over here. And then if I say 50 coulombs of over there, I mean 50 times that over there. Okay? A positive charge comes from protons. Protons have that many coulombs. Negative charge comes from electrons. Electrons have that many coulombs. Yes. Well, wow. We are going to do circuits. I mean, cool. If you think that's I mean, great. Yeah. Yeah. No, these numbers are wowza. Yes. Yes. Okay. Moving on. Oh, now for increased perspective, I'm watching the time. We're making progress here. It's good. And again, don't, and please, I know some people's brains are fried as they've admitted, and so's mine, as you can tell, or at least I'm certainly emotionally distracted, medically distracted. You don't have to like get your mind around all of these numbers or anything like that. The main thing is to realize that to get a force between two electrical objects, you multiply the amount of one times the amount of the other and divide by the distance squared, and then multiply by this universal constant. That's like the big takeaway so far that you'll need for Wednesday. And again, I'm telling you, Wednesday will be like practice with this kind of plug and chug. It won't involve calculus. Wednesday will not involve, for whatever that's worth. It's like multiplication. I'm not trying to be condescending, but I'm just saying, don't. Oh, yeah. Okay. But now for increased perspective on these numbers, like what I just told you was the charge of an electron and a proton. It's the same size, but different uh, directions, right? But now for perspective, like electrons and protons don't have the same mass. They don't. First of all, like the mass of an electron is like about 10,000 times smaller than the mass of a proton. Like there's the numbers right there. Like, okay, they're both very small. But the proton is 4 orders of magnitude. That means like 10,000 times bigger than the mass of an electron. But why I'm giving you those numbers is to say if all other factors were equal, this now kind of gets to what some of you were asking earlier in the class. If all other factors were equal, if you had like a electron over here and another electron over there, like separated by a few meters, to be clear, each electron has mass, the same mass, and has charge, the same charge. So the mass of one electron would automatically gravitationally pull on the mass of the other electron. So if nothing else were going on, and they would just like they would start, pulling on each other and coming together. But at the same time, the charge of one electron would push on the charge of the other electron uh, through electrostatic force. So they would push each other while electrically while they're pulling on each other gravitationally. Both would occur at the same time. Like they don't cancel each other out or anything like that. It'd be like a free body diagram with two forces in the free body diagram. So like, what does that mean? Like how, so the net force would be whichever one is bigger minus whichever one is smaller. And that net effect would win out and cause them to accelerate either toward each other or away from each other. Well, which one would it be? Well, if you just run the numbers, I'm not going to do this right now. I mean, we almost could, but if you just plug in the numbers into the equations I've given you with the constants written in, you'll find that because that electrical constant is so much bigger than that gravitational constant. Again, remember the electrostatic constant is 8.99 times 10 to the positive ninth. That's like 10 billion. Whereas the gravitational constant is 6.67 times 10 to the negative 11th. That's 100 billionth power. One is so much bigger than the other that when you run the numbers, you will find that the electrostatic repulsion is way bigger than the gravitational attraction. All other things being equal, the amount that an electron pushes away another electron at a given distance is roughly 10 to the 40th times bigger than the amount that it pulls toward. I don't mean just 40 times bigger. I mean 10 to the 40th times bigger, 40 orders of magnitude. So electrostatics in general is a much more dominant, powerful phenomenon than gravitation. Remember I said before, gravitation really starts mattering when the masses are big enough to really matter. Also, right, so why does gravity ever matter? How does gravity ever like take over electricity? The other thing about electricity, as I keep sort of implying, and as you know, is electricity comes in, or electric charge comes in two forms, positive and negative. So in a macroscopic object like a planet, for every electron that is in the sun for every electron that's in the sun pushing on every electron that's in the earth, there's also a proton in the sun pulling on the electron in the earth. In other words, macroscopically, generally speaking, whenever there's electrons, there's protons. So whatever repulsion exists electrostatically gets balanced perfectly by whatever attraction exists electrostatically. And so that's why with really, really big objects, what's left over is the gravitational effect. But if you get into tiny situations in the lab, and particularly if you can ever separate a bunch of electrons from their atoms, if you can start separating free, which you can't do that with protons unless you like break apart the nucleus and create a bomb. But electrons, as you know from chemistry, can be ripped out of their orbits, and you can ionize atoms, and you can create these things called free electrons, which just roam around by themselves. And you could put them in metals and send them from one place to another. So now you're looking at net amounts of negative charge that don't have any counterbalancing positive charge. So you can create electrical effects that are very, very powerful in the lab and in the home and in life. And ultimately, that's really why it's called electricity, as opposed to atomicity or protonicity or something like that, because all of these electrical effects that we ultimately look at are created with net negative. I mean, it could have been positive. It doesn't matter whether it's negative or positive. The point is that one type of charge gets gathered by itself and separated from the other type of charge. And that's where we get all these electrical effects, is ultimately through the motion of free electrons. Okay. Oh, yeah, yeah, yeah. Yeah, there is a certain, it is like alchemy. Yes, I'll just leave it at that. But yes, it's totally staggering. That's for sure. Um, okay, I'm gonna go on. Okay. Oh, yeah. So look at this for a second. I'm gonna say this in 1 second. Okay. 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 So now I want you to notice one thing though here. Um, I want you to notice one thing, how this plus and minus really works out really nicely. Again, what I'm about to say is important, not hugely important for Wednesday, but it is important for later. Notice that I say when you create, well, well, yeah. Yeah. Oh, no, no. All right, I'll just leave it. Remember we said you have like a point charge over here and a point charge over here. The first thing you do in your mind is you draw this little unit vector r hat that has a length of 1, but specifically points from q1 to q2, right? And then you take that unit vector and you scale it by the magnitude q1 times the magnitude q2 divided by the square of the magnitude r and multiply all of that by the k number, right? And so then that unit vector becomes a big force vector. Now, in the case of gravity, we then took that whole thing and multiplied it by a negative sign. So it flipped around and became attraction always. We don't do that here. We don't take the whole package and multiply it by a negative sign. But the positives and negatives are already built in because if one set of charges is a bunch of protons, they get a positive sign. But if it's a bunch of electrons, they get a negative sign. So look how this works. You take the unit vector and you scale it up by the appropriate amount, q1, q2 over r squared times k. And then, depending on what the signs of the charges are, the sign of the whole force will pop out. That is to say, if q1 and q2 were both the same sign, because remember, they're being multiplied, right? Q1 is being multiplied by Q2 in the denominator. So if Q1 has the same sign as Q2, you're going to get a positive sign. That means the whole force will be positive. That means we take the direction of that vector that's pointing from Q1 to Q2 and we leave it alone. If we get a positive sign at the end, we don't flip it. So that means Q1 would create a force that's pushing away from it onto Q2. But repulsion. But if one of the signs is different from the other, if it's a positive times a negative or a negative times a positive, then a negative sign will pop out. And that will mean that we take the force vector that we got and flip it around. So then it'll become a pull. Do you see what I'm saying is? I'm saying once you plug in the signs of Q1 and Q2, automatically the whole force will have a sign, either positive or negative, automatically from the multiplication of those two numbers. The whole sign, the whole force will have a sign, positive or negative. And so if the whole sign of the whole force is positive, is negative, that means it's like gravity. It'll be a pull. Q1 will exert a force back toward Q1. It'll pull Q2 toward it. But if the whole sign is positive, that means Q1 will push Q2 away from it. So it's a beautiful convention. It means we maintain that same idea that we started with gravity, which is from here on in, a negative force is a pull and a positive force is a push. And the positiveness or the negativeness will be automatically generated by putting in the signs of the two charges, this is why we call them positive and negative rather than red and green or something like that, because positive times a positive because a positive times a positive always makes the same thing as a negative times a negative, which is positive. Repulsion. Likes attract and opposite. No, opposites attract and likes repel. Do you see? Okay. Can I go on? Do you see what I'm saying? Can I go on? Thank you, Justin. All right. Awesome. Good enough for me. Okay. Now, one other thing I have to sort of tell you or warn you, this is partly a warning and partly a good news. That K number, 8.99 times 10 to the ninth. Yeah, okay. The 8.99 times 10 to the ninth. It's a little bit annoying that it's called K. So in a way, there's an answer to that, but also for other reasons. The truth of the matter is, and this will be printed on the sheet that you'll get Wednesday. The truth of the matter is that we often don't refer to it as K for reasons that emerge. We often call it 1/4 times pi times this other number that we define called epsilon naught, or in other words, also known as the permittivity constant. So that's a lowercase epsilon. It has a naught. I'm introducing it right now. I am not. Maybe you've seen it in chemistry, but I'm not assuming that. I'm saying there, and you don't have to memorize it, but you have to understand. There's a tiny, tiny number called called 8.85 times 10 to the negative 12th. If you, in other words, well, yeah. Well, no, I mean, I just said it. I can't say it. I'm saying if you take this number, 8.85 times 10 to the negative 12, and you multiply it by pi, and then you multiply that by 4, and you put it all under 1 in your calculator, or you hit like to the negative 1 on your calculator, right? You'll get, the calculator will spit out approximately 8.99 times 10 to the ninth. This looks like a more clunky, inconvenient way of writing the simple number K. It turns out, for reasons you'll see in Gauss's law, it turns out to be a more convenient way. It makes other things cancel later on. So I'm saying that this equation that right now we're learning this equation, the electrostatic force equation. We're learning, right? Everything I'm talking about right now is this equation in red at the bottom, right? But okay, well, you could do that. But I'm telling you, you have to get used to, whether you like this or not, you have to get used to the fact that, in fact, as physics gets more advanced and as we get into other laws like Gauss's law, actually the K is often written as 1/4 pi epsilon naught, where epsilon naught is this other tiny number, 8.85 times 10 to the negative 12. So you want to get used to, you need to be familiar with the fact that often this equation that I'm teaching you right now is actually often written this way. Okay, it looks more complicated. It looks more inconvenient. I apologize for that. It ultimately is more convenient. But okay, so this is equivalent. And you need to know that. Okay. Okay. Pause for a second. Okay. Uh, Let me think about that. I see your question in the chat. I'm actually a slight. I hear you. As of now, it's not a break. Yeah, you let. I'm not sure I can answer that right now, but I will say to everybody, the thing that you're going to do in the lab, actually, the board meeting you're going to do on the lab Wednesday, actually is the homework sheet that's right now due next Monday. If you do the board meeting properly, you will sail through a huge portion of the homework in that board meeting. The farther you get in the board meeting, the farther you will have gotten in the homework that, at least as of right now, is due next Monday. I can think about whether I'm changing that or not, but please know that too. And everything I'm saying here is to prepare you for this lab Wednesday. In fact, okay, wait, okay. Um, Sorry, I'm not distracted, but I am getting distracted, but not by that, by something else that's going on in the background and in my mind. Give me a sec. And my goal here, I want to give you a little bit more. I want you to be prepared for the Wednesday. We're not going to go to 1:30, but we're going to go a little bit longer. Um, just bear with me for a second. All right, yeah. Okay. Everything I just gave you is for like I keep saying, is for um the board meeting Wednesday. What I'm going to do now for some amount of time is continue this. I'm going to give you, just take these notes and listen. You will see once you get the sheet on Wednesday that everything you don't get to Wednesday in the lab in order to do the homework for Monday is what I'm addressing right now. You'll have to make the connection, but you will make the connection and you'll see how this is helpful. To be even more blunt or concrete, if it helps, the sheet you're going to get on Wednesday is like 3 sheets. Sheet 1 has like the equations explaining all this. Sheet 2 is sort of the plug and chug exercises. And then sheet 3 is the tricky part with vectors. Sheet 2 is what you'll get through in the board meeting Wednesday. Sheet 3 of it is what I'm about to show you how to do right now. Okay. Um, Okay. Let's say you have two source charges sitting. Okay, wait. Yes, I think, but I haven't said anything about potential yet, but yeah. Well, okay, so let me explain. Yeah. So let's say you got an XY coordinate plane. This is where the homework takes you for Monday. Say you've got an XY coordinate plane. You've got a source charge of capital Q1 sitting there at the coordinates 5, 4. It's got a positive 5 coulombs of source charge. But say you also have another source charge, like another bunch of now electrons sitting over here at the coordinates 10, 3, and they have a amount of source charge -2. And let's say there's a little, so now I make a lowercase q sitting at the origin. Let's say it has +1 Coulomb of charge. Like, wait, now suddenly we have 3? Like, what's going on here? Like, this entire time I've been talking to you, I've been talking about one thing making a force onto another. What I'm now raising, and that's what most of the board meeting will be about Wednesday, is just like one thing affecting another. But then, okay, wait, hold on. Well, that's what the origin, the coordinates of the origin are 0, 0. But so what I'm positing here is what happens if we have more than two charges? Like, how do we deal with all this stuff? Like, how is gravity always talked about the Earth and the sun and the moon and all these big objects that are made? Okay, 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 okay. How do people talk about gravity or electricity when they have anything more than just a dot and a dot? And I'm showing you now. I'm saying, what if we have 3 dots? Like, how does this work? Well, first of all, you got to talk about, like, what are we viewing as the source and what are we viewing as the test? Remember, I gave you that vocabulary like an hour and a half ago. Like, if you imagine Q1 is over here and Q2, they're both capital letters. Q2 capital is over here. But we've got this receiver guy, this 1 Coulomb of positive lowercase q charge that's sitting at the origin at 0.00. If we want to ask the question, okay, I want to make this very clear. Wait. If we view lowercase q as the test charge, the guy that's receiving the forces from anything and everything else around it. So Q, lowercase q, is like the receiver sitting there, in this case, at the origin of a coordinate system. Q1 is over here, and Q2, capital Q1 is over here, and capital Q2 is over here. I want to make clear to everybody, like, this is what I'm asking right now, and what you're going to be asked in effect in the homework when you're done with the board meeting Wednesday. What I'm not asking is, what is capital Q1 doing to capital Q2? Like, that could be a question. Like, there is something happening, but that's not the concern. That's not the issue. The issue is Q1 is pushing or pulling on lowercase q, and Q2 is also at the same time pulling or pushing on lowercase q. That's why I've placed q, lowercase q, at the origin of my coordinate system. Really, honestly, what I've really done is like I've centered a coordinate system on q, lowercase q, because I'm like trying to examine what is happening to q from capital Q1 and capital Q2. So the question is like, how do I do this? How, yeah, I ultimately want to know wait, okay. So, sorry. What I really want to know is what is the overall, like I want to know, yeah, what's the net electrostatic force experienced by lowercase q? In other words, what is the vector? I'm looking for a vector. We must compute the vector whose magnitude and direction tell us how hard and in what direction Q gets pushed or pulled, so I'll say shoved, by the combined effect of Q1 plus, or really, and Q2. That's what we're trying to figure out here. Well, wait. So no, what we're saying is we're looking at what the source is, or in this case, the combined sources are doing to the test. Like we're not going in the other direction. I mean, the other direction would be Newton's third law, but we are looking at what the sources are doing to the tests. So, um, so wait, hold on 1 second. Everything's getting. So how do we do this? I mean, I'm not going to do it all for you right now, but I'm going to set it up and show you. What we have to do is we have to add the vectors FQ1Q plus FQ2Q to yield the combined effect, like the net effect of Q1 and Q2 onto Q. So how do we do that? How do we add these two vectors? By the same methods that we ever added vectors in physics 203, whether it was displacements or velocities or forces, we add components. And this is where free body diagrams and component free body diagrams and all of that come in. So in other words, let's look at the picture again. Here's the picture. Q1 is a positive charge, is a positive source charge over here. Lowercase q is also positive. So Q1 would push on, wait, sorry, and I'm going to ignore the chat for a little bit because I'm sort of rushing. I just want to try to land this plane as best as I can and let you guys go a little bit early. So forgive me let me just, and also I know I'm getting frenetic and sort of distractible. So let me so I apologize. I'm just going to do this for a second. Um or possibly for the remainder. Q1 is pushing on lowercase q. How do I know pushing? Because they're both positive, right? So there's going to be a vector that lands on Q2 that looks something like this. Where did I get that from? I mean, I imagined the line, the R, connecting Q1 to Q, and I extended it out from lowercase q because Q1 is going to push Q in a certain direction, push it along that line. So there's going to be a force on lowercase q from Q1. But also Q2 is interacting with lowercase 2. Only Q2 apparently is a negative source charge. Negative times a positive yields a negative. Like that's going to make a pull, right? So there's going to be a pull on lowercase q that looks like more like that. It's it's extended, it's pointing along the line that would connect Q2 to lowercase q, but it's pulling, so it's pointing towards Q2. Also, notice I made it smaller. Why did I make it smaller? I mean, it's not perfectly to scale, but I have a feeling it's a lot smaller than the other one because Q2 is a much smaller magnitude of charge and it's much farther away, right? So I've got two effects on lowercase q, a big force pushing it down into the left and a small force pulling it up into the right. It's those two vectors that I'm going to add together. Right? We're adding these two vectors together. If we put them tip to tail, well, I'll do that. If we want to see a general picture of what's going on, it would look like that. And the answer would point from the original tail to the final tip. And I apologize again. Maybe I may not be able to let you go early. I want to at least get this set for you to be able to do the. I'm not going to do all the details, but I want you to see the big picture so you can do the homework. I'm trying to let you go early, but if I can't, I won't. Because we did have a break. Okay. So the big picture here is, and again, let me back up. What am I trying to do? Everything I was saying for the beginning of the period was like how one point charge interacts, exerts a force on one other point charge. And again, that's the bulk of what you're going to be focusing on for the board meeting tomorrow. Now what I'm at, you'll see it in the sheets from the board meeting, but I don't think you don't need to get very far with what I'm talking about right here. Well, I don't know how far you'll get with this Wednesday, but any amount that you get with what I'm talking about now is just going to accelerate your completion of the homework that all of this is due next week. So the distinction that I'm making right now is, what if you have more, if you have a bunch of charges, if you have two charges pulling or pushing on one, that's what I'm talking about right now. And I'm saying that what you have is vector addition. One charge is pushing that way, another charge is pulling that way. So you got to put the two vectors in your mind to picture what's going on. You put the two vectors tip to tail, and the result would be in other words, at the end of the day, that little q at the origin will be shoved somewhat southwest, like down and to the left. not quite as much as Q1 is pushing it, not quite as much, because Q2 is pulling it back. It's like fighting against it a little bit. But really, if you just step back and look at the numbers, Q1 is kind of dominating the Q2 situation. So mostly what's happening is the result is going to be this blue dotted line that basically shoves Q, lowercase q, to the left and down, south and west. The only issue left is like, how do you get the numbers, which you are expected to get? Here's how. And I'm just going to set this up for you, and then we're going to stop. Oops. Okay. So we're going to zoom in, like that first vector. The first vector looks like this. It has some amount in the x direction, some amount in the y direction. There's this angle, we'll call it theta 1, because this is the force from Q1. Well, the force is the magnitude is KE Q1 Q over R squared. That's the magnitude. This, the horizontal piece, so we'll call that F Q1Q. The x component would be the whole thing, the hypotenuse, times the cosine of the angle. And the y component, of course, would be the whole hypotenuse times the sine of the angle. The whole hypotenuse is what you get when you plug all those numbers in. You know, K, Q, like all the given numbers. This is a subscript, this is a subscript. So the only question is, what's that angle, or what's cosine of theta, and what is cosine of theta? And we're going to stop once I show you how to do one, you'll know how to do the rest. What's the cosine and sine of the angle? Well, cosine of the angle equals the adjacent over the hypotenuse. The adjacent is, if you look at the picture, the adjacent is, if we're doing this first, from the Q1 is at the coordinates 5, 4. So the adjacent side, the x component of that triangle is 5. And what's the hypotenuse? The hypotenuse is the square root of 5 squared plus 4 squared, if you see what I'm saying. If you follow that, that's the hardest part in the whole problem. And the sine of the angle would be the opposite over hypotenuse. The opposite is 4, and the hypotenuse is 5 squared plus 4 squared. So this would all be the components of what we're going to stop in a second. This is all the components of one force take the other force and do, okay, KQ2 over R squared to this, all these R's that I'm talking about. This is all, yeah, this is all R1. Do the exact same thing to the other force, only do the other angle and the other magnitude, etc. So at the end of the day, you'll have at the end of the day, you'll have an XY chart. You'll have an X component of one force and a different X component of, and a Y component of one force. And you'll have a different number, an X component of the other force, and a different number, and a Y component of the other force. You add the components up. You add up the X components, and you add up the Y components. Just like we did with displacements and velocities last semester. I'm saying that each individual force vector you break up into X component and Y component by doing cosine and sine. You add up all the X's, you add up all the Y's, and in the end of the day, you'll have, at the end of the day, you'll have one big X added with one big Y, and you take the Pythagorean sum of the two, and that will be your total magnitude, and the total direction will be the arc tan of the opposite over the adjacent. Now, I said that sort of quickly. That's a lot. Again, let me say, this is what, yeah, theta is relative to, theta is always relative to a horizontal, to the x-axis. Theta is always measured from the x-axis. I mean, that's a good question. Always from the x-axis. So this procedure I just sort of said sort of quickly, this is how you'll do the end part of the force question that will be handed out on Wednesday. You'll probably only start this part on Wednesday, and that's fine. It's a lot, I know, but but this is the notes that you want to consult when you try to do the homework for next Monday. I know as usual, I kind of ended with like an overload. I'm overloaded too. But most of what we said today, just one object affecting one other object, is that, and mostly just magnitudes, not even getting bogged down in the negative signs or the unit vectors, mostly the magnitudes of one object, one test charge affecting one other is what you're going to do on Wednesday. You've all been incredibly patient and incredibly diligent and invested. And I think successful. We'll see. I hope. But I thank you all very much. I will see you Monday. Yes. And goodbye. Have a great rest of the day and
Thank
stay
you.
safe and work. Thank you. Thank you.
Bye.
Bye. Thank you. Thank you. Thank you. Thank you.